The cosmos is stretching apart, and it's doing it faster every second. There's a force behind that dark energy. It's causing this runaway acceleration. And it makes up most of our universe. The evidence for this is pretty incredible, and it points to a fundamental gap in our laws of physics. Scientists made this discovery. It was shocking, and it tells us something about the ultimate fate of all existence. A universe governed by a force like that. It makes you wonder about our place within it. The idea of a stable cosmos was comforting. It gave us a fixed backdrop, a permanent stage. That wasn't just old philosophy, it was the accepted science for a very long time. Then you had Edwin Hubble, up at Mount Wilson in the 1920s with his telescope. He was looking at these faint, fuzzy patches, nebulae, and he found two things. First, he proved they weren't just clouds in our galaxy. They were other galaxies, entire islands, incredibly far away, that changed the scale of everything. But the second finding was bigger. He looked at the light from these galaxies, and it was shifted, redshifted, like the sound of a siren dropping as it moves away. That meant the galaxies were all moving away from us, and then the real point, the farther away the galaxy, the bigger the redshift, the faster it was receding. That relationship became Hubble's law, and the conclusion was unavoidable. Space itself was stretching. The universe was expanding. Think of dots on a balloon. When you blow it up, every dot moves away from every other dot. The farthest ones seem to move the fastest. So that was the new picture, a dynamic, growing arena. Starting from what we call the Big Bang, and from that, a forecast seemed logical. Gravity pulls things together. So if everything started rushing outward, all that matter, stars, galaxies, its gravity should be pulling back. Acting as a brake, the expansion had to be slowing down. That was the narrative for decades. A universe born in fire, now gradually coasting to a stop. That idea guided cosmology, but the universe has a way of defying intuition. The story was about to turn, in a way so strange it would force us to rewrite the laws themselves. For years, astronomers were trying to measure the cosmic slowdown. They focused on a specific kind of stellar explosion, the Type 1, a supernova. These are consistent. Like a light bulb with a known brightness, so by seeing how dim they looked from Earth, you could get a precise distance, and by looking at the redshift of their light, you could get their speed. It was a built-in speedometer, so two major teams got to work, one led by Saul Perlmutter, another by Brian Schmidt and Adam Rees. They were looking deep into the past at supernova billions of light years away. The idea was to see how much the expansion had slowed over that time. The expectation was clear. The ancient, distant ones would show a faster, younger universe. The closer, more recent ones would show the slowing from gravity. They gathered the data, they plotted the points, they waited for the curve to show the braking. But the curve didn't bend that way. It showed the opposite. The most distant supernovae were fainter than they should have been, which meant they were farther away than predicted. And if they were farther away, it meant the universe hadn't been slowing down. It had been speeding up. The expansion was accelerating. It's like throwing a ball straight up. You expect it to slow, stop, and fall back. But instead, it just keeps going up, and it goes faster the higher it gets. That was the level of shock, a complete reversal. A plot twist in reality. Both teams, working separately, found this in 1998. The universe wasn't just expanding, it was flying apart faster and faster. Pushed by something that overpowered gravity, the discovery won the Nobel Prize, and it forced a rewrite of the cosmic inventory. That something was given a name. Dark energy, it wasn't matter, it wasn't radiation, it was a property of empty space itself, a kind of anti-gravity in the vacuum. The calculations that came after were more startling. This dark energy wasn't a minor player. It was the dominant component, about 68% of everything. All the stars, galaxies, planets, every atom. All that normal matter is less than 5%. The rest is this dark energy and its cousin, dark matter. So this force, the one we never knew existed, the one tearing the cosmos apart faster every second. It's not a side effect, it's the main character, it's the stage itself, and it's reshaping the destiny of everything on it. The story of dark energy really goes back to Albert Einstein. In 1917, he was working with his new theory of gravity, general relativity. He applied it to the whole universe, and his equations, they were beautiful, but they had this problem. They said the universe couldn't be static. It had to be moving, either expanding or contracting. But to Einstein and to everyone then, the universe was eternal. It was unchanging, so he introduced something, a kind of fudge factor. He called it the cosmological constant. It was a tiny, repulsive force built right into space. Its only job was to counteract gravity, to hold everything in a perfect, frozen balance. It was a mathematical trick, just to keep the universe static. Then Hubble made his discovery. The universe wasn't static, it was expanding. Einstein saw that and famously called the cosmological constant his greatest blunder. He took it out of his equations. He said it wasn't needed, so that was it. A mistake corrected, but decades later they found the supernova, and they showed the expansion wasn't just continuing, it was accelerating. So scientists looked back. They looked at Einstein's old idea, that constant he threw away, that repulsive force in space, and they realized it wasn't a mistake. It was a prediction. The cosmological constant came back. It became the leading candidate for dark energy. The simplest idea is that empty space isn't really empty. Quantum physics says it's a sea of virtual particles, popping in and out of existence. This quantum foam should have an energy, a pressure, and in Einstein's math, that vacuum energy acts exactly like a cosmological constant. It gives a uniform push, a push that gets stronger as space itself expands. You can picture space as a stretched grid. Galaxies are on that grid, pulled together by gravity. But the grid itself, it's springy. As it stretches, it stores more repulsive energy. The bigger the universe gets, the stronger that spring pushes. It accelerates the expansion. It's an elegant fit for the data, so elegant it creates a huge problem. If this is the answer, then why is the number so incredibly small? When you calculate the expected energy of the quantum vacuum, the number is enormous. It should be 10 to the 120th power stronger than what we actually see. That's not a small error. It's the worst prediction in science, so we're left with this. Either our understanding of the quantum vacuum is completely wrong, or this simple constant, it's not the final answer. This mismatch isn't a small error. It's a chasm, a gap so wide it's hard to even describe. The number is 1 with 120 zeros after it. That's how many times stronger our quantum theory says the vacuum energy should be, compared to the dark energy we actually see. Think about the energy in a single breath, and then the energy in all the stars in every galaxy we can observe. The gap is bigger than that, even bigger. This is the cosmological constant problem. It's a theoretical nightmare. It means one of two things. Either our understanding of the quantum world is just wrong when we scale it up to the cosmos, or there's some unknown cancellation at work. Some perfect, fine-tuned balance that zeroes out almost all of that colossal energy, leaving behind just this tiny whisper. The whisper we call dark energy. Neither option is comfortable, not for physics. Imagine your theory predicts a mountain of energy so huge it would have torn the universe apart instantly. But when you look, you see a gentle hill. A slope so slight it took billions of years to even notice it. So where did the mountain go? Was the blueprint for the mountain itself flawed from the start? Or was there some hidden architect who carved almost all of it away, leaving just this specific, subtle contour behind? This is the clearest sign. Our two greatest theories are talking past each other. Quantum mechanics rules the tiny world of particles. General relativity rules the vast cosmos, gravity, and space. Both are incredibly successful in their own realms. But they speak different languages, and when they try to describe the same thing, the energy of space itself, they give us this answer, this absurd, impossible answer. The vacuum catastrophe tells us we're missing the translator. We're missing the theory that bridges the micro and the macro. Until we find that, dark energy is just a placeholder. A name for an effect, a name for a mystery we don't yet understand. Faced with that gap, physicists have had to look beyond Einstein's constant. It's opened up a whole new frontier of ideas. The simplest alternative is quintessence. The idea is that dark energy isn't a fixed property of space, but a kind of fluid, a dynamic field that fills everything like a fifth element. And unlike a constant, this field could change. Its strength could ebb and flow. It could have been weaker in the past, stronger now, or maybe it fades in the future. Quintessence introduces a story. It means the acceleration we see today might not be the final word. The fate of the universe becomes a question again, depending on how this field evolves. It's compelling because it offers a way out of the fine-tuning problem. Maybe the energy is small now, not by coincidence, but because that's just where we are in its cycle. Then there's a more radical path. What if the problem isn't with dark energy, but with gravity itself? That's modified gravity. Einstein's theory has passed every test from Mercury's orbit to the bending of light. But those tests are within galaxies or clusters. What if, on the scale of the entire universe, the rules change? What if gravity weakens differently over these immense distances? In this view, the acceleration isn't being driven by a new force. It's an illusion from our misunderstanding of gravity on the grandest stage. Like discovering the rules of perspective we've used are subtly wrong, making distant objects seem to behave strangely. Proving this would mean revising one of the most successful theories in history, and the proposals get even more exotic. Some theories suggest our three-dimensional universe is a projection, a hologram, of information stored on a distant two-dimensional surface. In that framework, dark energy could be a side effect of how that information is encoded. Others look to string theory, with its tiny vibrating strings and extra hidden dimensions. Maybe dark energy is a signal from these other dimensions, a pressure leaking into our own. These ideas sound like science fiction, but they're serious attempts to solve a serious problem. They all make one crucial promise, different predictions. A simple constant says the acceleration rate should be steady. Quintessence says it might be changing. Modified gravity predicts specific alterations to how galaxies cluster and move. These aren't just philosophical debates, they're blueprints for experiments. They give astronomers a target, a way to listen for the specific heartbeat of the cosmos and diagnose what's making it race. That whisper of dark energy, it leaves a signature. A signature written in the stretching of space itself. To measure that, you need a cosmic ruler. The best one we have is a stellar catastrophe, the Type 1, a supernova. It's a standard candle, a cosmic light bulb with a known wattage. Here's how it works. A white dwarf star, the leftover core of a sun-like star, pulls material from a companion. It reaches a critical mass about 1.4 times the mass of our Sun. Then it triggers a runaway thermonuclear explosion. This explosion is so consistent. Every single one peaks at nearly the same intrinsic brightness. So when we see one in a distant galaxy, we know how bright it truly is. We measure how dim it appears to us. The difference gives us its distance with incredible precision. It's like seeing a familiar light bulb far out in a foggy field. You know its true power, so by how faint it looks, you can calculate exactly how far away it stands. But distance is only half the story, the other half is speed. As space expands, it stretches the light traveling through it. It shifts the light toward the red end of the spectrum. The more the light is stretched, the faster that galaxy was moving away when the light left it. This redshift is the universe's own speedometer. So for each supernova, we get two numbers: a precise distance and a precise speed from a specific moment in the past. By looking at supernova at different distances, which means from different eras in cosmic history, we can plot the expansion rate over time. We can watch the universe grow up, and that plot, built from these dying stars, revealed the shocking acceleration. The most distant, ancient explosions were fainter than expected. That meant the universe had to stretch more than we thought to make them look that dim. The expansion had not been slowing, it had been speeding up. This supernova data is the most direct evidence. But it's not alone. It forms one of three pillars. The second pillar is the cosmic microwave background, the afterglow of the Big Bang. This faint, cold light fills the entire sky. Its subtle patterns are a baby picture of the infant universe. By studying the tiny temperature variations in this light, scientists can deduce the geometry of the cosmos. They can find the total amount of matter and energy. The results are clear. The universe is flat. Normal matter and dark matter together only make up about 32% of everything. The rest, that missing 68%, is the smooth, repulsive energy needed to match the supernova observations. The third pillar comes from mapping the large-scale structure of the universe. By surveying millions of galaxies, measuring how they cluster together under gravity, we can see how structure has grown over billions of years. Dark energy acts as a counterforce to gravity. It suppresses the growth of these cosmic webs. The maps we see today show exactly the level of suppression we would expect. If dark energy started dominating the cosmic energy budget a few billion years ago. Three completely independent lines of evidence, from the death throes of stars, the first light of creation, and the grand architecture of galaxies, they all point to the same conclusion. An unknown force is woven into the fabric of space. Its gentle, relentless push is writing the final chapters of our cosmic story. The data shows the universe accelerating. But where it ends up, that's not settled yet. The fate of everything depends on what dark energy actually is. If it's Einstein's constant, just a fixed property of space, then the future has a kind of logic to it. A steady, relentless pace. The expansion keeps accelerating, but at that same steady rate. Galaxies outside our local group will race away. Their light gets stretched until we can't see them anymore. Our observable universe becomes this lonely island. Just a few galaxies bound by gravity. Star formation stops, the gas gets too thin, existing stars burn out. Black holes, over incomprehensible time, they evaporate. The cosmos becomes a vast, dark sea, isolated particles, cooling forever. That's the big freeze. The heat death, an end not with a bang but with a whisper, a silent one. That's the gentlest possibility. But if dark energy is dynamic, something like Quintessence, it could get stronger. Its repulsive push could increase. Then the acceleration doesn't just continue, it intensifies exponentially. First, the force overcomes the gravity holding clusters of galaxies together. They get flung apart, then it goes after individual galaxies. The Milky Way would be torn apart, stars scattered into the void. As the force grows, it reaches into solar systems. Pulls planets from their stars, then it turns on the planets themselves, overcomes the gravity holding them together. Mountains lift from the surface. The Earth comes apart. In the final moments before time loses meaning, the force reaches into the fabric of matter. It overcomes the forces binding atomic nuclei. Overcomes the forces holding electrons in orbit. Every molecule, every atom, every fundamental particle gets pushed infinitely apart from every other. That's the big rip, the fabric of reality shredded by the expansion. The difference between these fates, it's not a small detail. It's the difference between a slow fading of the lights and the sudden, total dissolution of the stage itself. And the deciding factor is a number, a parameter called W. If W equals exactly -1, dark energy is a constant. The big freeze awaits. If W is less than -1, if the force grows, then the clock is ticking toward a big rip. Current measurements put W incredibly close to -1, consistent with a constant, but the uncertainty in our measurements, it leaves the door open. Just a crack to the more violent possibility. Understanding which path we're on means looking deeper, measuring more precisely, mapping the universe's contents with even greater care. Listening for the subtlest changes in the heartbeat of expansion. The answer is out there, written in the light of dying stars, in the ancient whisper of the cosmic microwave background. Our task is to read it before the final page turns. The universe has a budget, a kind of cosmic pie chart, and our share, the part we actually understand, is just so small. All the stars, all the galaxies, every planet, every living thing, all of that normal matter, everything we can see, it adds up to 5%. 5% of everything that's there. It's just the visible tip. Then there's the next piece, about 27%, that's dark matter. It's this invisible scaffolding. We can't see it, it doesn't interact with light. But we know it's there because of gravity. Its pull is what holds galaxies together, keeps them from spinning apart. It guides whole clusters of galaxies. It's the framework, the cosmic glue. Without it, galaxies wouldn't exist. We don't know what it is, but we can measure its gravity everywhere, and then the rest. The biggest piece, 68%, that's dark energy. It's not matter. It's a kind of negative pressure, a push built into space itself. So dark matter pulls things together, but dark energy pushes them apart. And because it's tied to space, as the universe expands and makes more space, you get more dark energy. Its influence grows. So now, in this era, it's the dominant force. It's the majority of the budget. It's what's driving the whole evolution of the universe. So this pie chart, it shows something. For all our science, our telescopes, we really only understand that 5%. The other 95%, the dark sector, it's a mystery. We see its effects, we map its influence, but we don't know what it is. Dark energy isn't some side note. It's the main ingredient. The stage itself is active, it's dynamic, and it's writing a story we're just starting to read. Every observation is another clue, trying to figure out what the other 95% of reality actually is. Geometry is about space. It's the language of space, and our universe is accelerating, which tells us something about its shape. In general relativity, the amount of stuff in the cosmos, the density of matter and energy determines the geometry. There are three possibilities. If the density is too high, space curves back on itself like a sphere. Parallel lines would meet. That universe is finite with no edges. You could travel forever on it. If the density is too low, space curves outward like a saddle. Parallel lines would diverge. But if the density is just right, at a critical value, space is flat. Euclidean, the rules from school apply. Parallel lines stay parallel. A triangle's angles add to 180 degrees. For decades, cosmologists wondered which one we lived in. The answer came from the oldest light, the cosmic microwave background. That afterglow from the Big Bang isn't uniform. It has tiny variations in temperature, like an imprint of the early universe's lumps. By measuring the size of those patterns, scientists could deduce the geometry. The results were clear. To a precise degree, our universe is flat. That was a monumental finding. But it created a puzzle. For the universe to be flat, the total density has to be exactly at that critical value. Yet when astronomers added up all the normal matter and dark matter, it only came to about 32% of what was needed. Something was missing. A huge part of the cosmic budget was unaccounted for. This is where dark energy enters, not just as an explanation for acceleration, but as the missing piece of the geometric puzzle. That 68%, the repulsive energy of space, fills the gap. Add it to the matter, and you hit the critical density perfectly. The flat geometry from the ancient light and the accelerating expansion from dying stars, they are two sides of the same coin. They tell a consistent story. Our universe is flat because dark energy exists. Its push isn't an add-on, it's a requirement for the shape we observe. So we have this cross-check. Two independent probes, one from the universe's first light, one from stellar explosions, converge on the same recipe. 5% atoms, 27% dark matter, 68% dark energy. That recipe gives a flat geometry and a runaway expansion. The model works, the numbers fit, yet the main ingredient, the one that defines the shape and fate of everything, remains a mystery. We've mapped the consequences with precision, but the cause hides in plain sight, woven into the empty space between the stars. That ancient light is the most direct line we have back to the beginning. It's the cosmic microwave background, a faint, cold glow that fills every direction. It's the afterglow of the Big Bang. When the universe was very young, it was a searing, opaque plasma. Light couldn't travel through it. Then, about 380,000 years after the start, it cooled enough for atoms to form. The fog cleared. And that first burst of light, released in every direction, has been traveling ever since. Over 13 billion years, the expansion of space has stretched that light. It's cooled it down from a blinding white to a faint whisper in the microwave part of the spectrum, just a few degrees above absolute zero. That's the CMB. It's the oldest picture we have, a snapshot of the infant cosmos, but it's not a smooth picture. When we map it with precision, like the Planck satellite did, we see it's mottled. It has tiny variations in temperature, hot spots and cold spots, differences of just a few millionths of a degree. These aren't flaws, they're the most important features in the sky. They are the seeds of everything. Those tiny ripples in temperature are tiny ripples in density, slightly denser patches where gravity had a little more to work with. Over billions of years, those patches grew. They pulled in more matter. They became the first stars, the first galaxies, the clusters and cosmic webs we see. So by studying the pattern of these spots, their size, their distribution, cosmologists can read the blueprint. They can deduce the universe's geometry, its total density, its recipe of ingredients. The pattern tells a precise story. It confirms the universe is flat. It pins down the amount of normal matter, and it reveals the amount of dark matter, which provided the gravitational scaffolding for those seeds to grow. But the pattern also revealed something else, something missing. To get the geometry to come out flat, the total energy density had to be exactly right. The matter they found, normal and dark, only accounted for about a third of what was required. The blueprint demanded another component, a smooth, uniform energy that didn't clump like matter. That missing component is dark energy. The CMB tells us that in that infant universe, dark energy was negligible, a tiny fraction. The universe was dominated by matter and radiation, its expansion slowing under gravity's pull. But as the universe grew, matter diluted. Dark energy, tied to space itself, did not. Its relative influence grew. The data from Planck pinpoint the moment of transition. About 5 billion years ago, the density of dark energy finally matched, then surpassed, the density of matter. From that point on, the repulsive push of empty space became the dominant force. The epoch of accelerated expansion began. The universe's brakes were off and its engine was engaged. That transition is written in the oldest light we can see. A whisper from creation telling us not just how it all began, but forecasting the strange, runaway future we're in. For most of its life, the universe was actually slowing down. Gravity was in charge for something like 9 billion years, every galaxy pulling on every other galaxy. All that dark matter, too, just putting a brake on the whole expansion from the beginning. It was still expanding, but that expansion was getting slower and slower. The future looked like a long, gradual coast, but the balance was shifting. Quietly, because as the universe got bigger, all the matter and radiation inside it thinned out. The density dropped, but dark energy, if it's a property of space itself, its density doesn't drop. It stays constant, so you get more space, you get more dark energy, but the amount in any given volume is the same, and so matter's influence fades over time. But dark energy's push, it doesn't fade, it just waited. Its moment came when the density of matter finally fell below the density of that constant energy in space. The calculations put that transition, that turning point, at about 5 billion years ago. To put that in perspective, our solar system was already here. Earth was here, life was well established, so while life was evolving on this planet, the whole cosmos was crossing this invisible line. The brakes came off. The accelerator went down, and it's been down ever since. Finding that exact moment isn't just history, it's a test. If dark energy is Einstein's cosmological constant, then that takeover was smooth. Inevitable, it happened right at that time because before that, its influence was just too small to see. But if dark energy is something dynamic like Quintessence, then its behavior in the past could have been different. Maybe it was stronger, maybe it was weaker, maybe the transition happened earlier or later. That timeline, the precise moment darkness took over, tells you what this force actually is. That's why astronomers are building these huge maps now, maps of the large-scale structure of the universe, charting billions of galaxies across cosmic time. They're looking for the imprint, the subtle imprint, of dark energy's growing influence on how galaxies and clusters form. By seeing how the formation of structure was suppressed over the eons, they can trace the rise of this repulsive force. They're writing the biography of dark energy, Chapter 1, A Whisper in the Early Cosmos, Too Faint to Matter, Chapter 2, A Rising Tide that Finally Matches Gravity's Pull. And then Chapter 3, The Dominant Force, the force that dictates the future now. We are living in Chapter 3, but to understand the whole story, you have to read the earlier chapters. And those chapters are written in the ancient light, in the fossilized structure of everything. There's another ruler out there, built into the universe itself. It's a fossilized sound wave. In the very early cosmos, the first few 100,000 years, it wasn't quiet. It was this hot, dense plasma, a soup of particles and light all bound together. And in that fluid, gravity would try to pull matter into clumps, but the radiation pressure was so intense it pushed back. That created a tug of war. Pressure waves rippling out from any slight over density, actual sound waves moving through the primordial fire. Then the universe cooled past a certain point. Atoms formed, the light decoupled, streaming away as the cosmic microwave background, and the sound waves they just froze, stopped right where they were. Those ripples got imprinted into the matter distribution, a subtle spherical shell pattern, a specific scale stamped onto the cosmos, about 500 million light-years across. That's the Baryon acoustic oscillation, a single note from the Big Bang preserved. As the universe expanded, that frozen wave pattern expanded with it. Carried along with the ordinary matter, the baryons. So now, when we map millions of galaxies, it's not just random, there's a subtle statistical preference. Galaxies are slightly more likely to be separated by that specific fossilized scale. It's like dropping pebbles in a pond, letting the ripples freeze, and then tracing where all the ice crystals settled. That frozen ripple is our standard ruler. We know its true size from the physics of the early universe, and by looking at galaxies from different eras, we can see how that ruler appears to us. If expansion has been steady, the ruler looks one size in our measurements. If expansion has been accelerating, the ruler at great distances appears more stretched than we'd expect. It's a purely geometric test. It doesn't rely on stellar brightness or the physics of explosions. It relies on the pattern left behind by the first music of the cosmos. And what does this fossilized sound wave tell us? It confirms the supernova story with remarkable precision. The BAO measurements show the same expansion history. They pinpoint the same transition from a slowing to an accelerating universe. They give the same constraints on the amount of dark energy. It's a completely independent line of evidence from the large-scale clustering of galaxies. Singing in harmony with the light of dying stars, this convergence is powerful. It means the acceleration isn't an artifact of one method. It's woven into the geometry of space and the distribution of matter itself. The echo of creation is telling us the same strange tale as the flash of stellar death. The universe is being pulled apart by a force we can't see, and every cosmic messenger we consult agrees on the verdict. Light bends around things we can't see. That's gravitational lensing. Einstein said mass curves space-time. So light from a distant object, if it passes near something massive, its path gets bent. Like a galaxy cluster, that strong lensing you see big arcs, rings of light, but there's a weaker version, more subtle, weak gravitational lensing. Where light from countless distant galaxies isn't warped dramatically, just sheared a little, stretched not by one big object, but by the vast webs of dark matter. The cosmic scaffolding, every line of sight out there goes through it, so the light from billions of galaxies carries a tiny imprint, a signature of all the dark matter it passed through. We can measure that by surveying huge areas of sky with precision. Telescopes look at the shapes of millions of faint, distant galaxies. Statistically, they should be randomly oriented. But if they show a coherent, slight alignment, a preferred direction of stretching that tells us something's distorting them, the gravitational pull of dark matter in between. It's like looking through a warped window. The imperfections in the glass twist the images behind it. Measure those tiny twists, and you can reconstruct the shape of the glass. Map the distribution of the dark matter. That gives you a three-dimensional mass map, a chart of the cosmic skeleton, and it's not a static picture. Galaxies at different distances show the dark matter at different eras. That's where it connects to dark energy. Dark energy pushes against gravity, suppresses the growth of structure. In a gravity-only universe, dark matter clumps would grow denser over time. But if dark energy is pushing things apart, it's harder for clumps to form. The growth of the cosmic web gets stunted. So by measuring how clumpy the dark matter is at different epochs, how much structure has grown over billions of years, you get a direct read on the strength of that opposing force. Weak lensing surveys are a cosmic census of structure growth, measuring how well gravity has built the universe against the tide of dark energy. It's a crucial line of evidence. It doesn't rely on supernova or ancient light patterns. It relies on light distorted by the invisible stuff. When you combine these lensing results with supernova data and cosmic microwave background measurements, they all tell the same story. They constrain dark energy's properties, narrow down what it could be, how much there is, how its influence has changed. It's a convergence, using the warping of space to probe the force that's stretching it. The cosmic picture has this elegance to it, but there's a crack in it. The numbers don't line up. There's a puzzle, the Hubble tension. It's a disagreement about how fast the universe is expanding right now. And it comes from two different ways of looking at things. One way looks back to the very beginning, the cosmic microwave background. The Planck satellite gave us this incredibly precise measurement of the early universe. From that baby picture, you can run the cosmic film forward. You use the standard model dark matter, dark energy as a constant to predict what the expansion rate should be today. That prediction comes out to about 67 kilometers per second per megaparsec. That's the unit. It means for every 3.26 million light-years you go out, galaxies are moving away 67 kilometers per second faster. The other way looks at the universe around us now, using supernova as standard candles, using pulsating stars, cepheids. These are local speedometers. They give a direct present-day measurement, and the answer they give is different. It's higher, about 73 kilometers per second per megaparsec. The difference is small, just a few percent, but in cosmology, where measurements are now so precise, that gap is huge. It's many times larger than the estimated errors from either method. So it's likely not a mistake, it's a tension, a persistent disagreement between the infant universe and the adult universe. It's like having two clocks. One was set at the moment of creation and has been ticking forward perfectly. The other you built and calibrated today, and they tell different times. Both clocks seem to be working flawlessly, so the problem might be with our understanding of time itself, or in this case with our model of cosmic history. This Hubble tension, it's more than a technical glitch. It could be a signal, a hint that something in our standard recipe is incomplete. Maybe dark energy isn't a simple constant after all. Maybe it evolved in a way we haven't accounted for, or perhaps there's another ingredient, some unknown form of radiation or particle that briefly flared in the universe's adolescence, changing the expansion history just enough to throw off the prediction. Some theorists even suggest the laws of physics themselves might have been slightly different in the distant past. These aren't small ideas, they're potential revolutions waiting in the data. This tension adds a profound urgency to every new telescope, every new sky survey, because if the crack is real, it's our best clue for finding what's missing. It's the universe telling us in its quiet, mathematical language that the story is even stranger than we thought. The Hubble tension is a puzzle. It needs sharper tools. We need to see the universe with a clarity we've never had. That's why the next decade is so pivotal. A new generation of observatories is coming online. Around the world and in orbit, their mission is to map the cosmos with staggering detail, so the subtle fingerprints of dark energy can't hide anymore. On a mountain in Chile, the Vera C. Rubin Observatory is getting ready. It's preparing for its legacy survey of space and time, a massive mirror, an enormous camera. It will scan the entire southern sky night after night for 10 years. It won't just take pictures, it will make a movie of the universe. It will detect billions of galaxies and track how their light changes. It will find millions of supernovae, building a colossal catalog of those standard candles to trace the expansion history with unprecedented precision. It will measure the weak gravitational lensing of countless galaxies, creating the most detailed map of dark matter ever made, and it will chart the Baryon acoustic oscillations. That fossilized sound wave across an immense volume of space. The scale of data is almost incomprehensible, a flood of light, a deluge of information, from which we hope to sift the truth. Meanwhile, from a telescope in Arizona, the Dark Energy Spectroscopic Instrument is already at work. DAISY isn't taking pretty pictures. It's collecting spectra. It uses 5,000 tiny robotic arms. Each one positions an optical fiber pointed at a single galaxy or quasar. These fibers capture the light and split it into a rainbow, revealing the precise redshift. The goal is to map the three-dimensional positions of 40 million galaxies and quasars. This will give us the largest, most precise map of the large-scale structure of the universe ever created. It will measure the BAO scale with exquisite accuracy across different cosmic eras and track how the clustering of galaxies has been suppressed by dark energy's push. Our view from the ground is powerful, but Earth's atmosphere blurs the finest details. To see the most subtle distortions from weak lensing, we need to go to space. The European Space Agency's Euclid telescope is now on its mission. It's designed specifically to measure the shapes of over 1 billion galaxies with incredible sharpness. By charting this cosmic shear across 10 billion years of cosmic history, Euclid will trace the growth of structure and the influence of dark energy. With a level of systematic control that's impossible from the ground, and soon it will be joined by NASA's and Nancy Grace Roman Space Telescope, with a field of view 100 times larger than Hubble's. Roman will perform giant surveys at infrared wavelengths, peering through cosmic dust to see the universe's structure. It will use all three primary techniques: supernova, weak lensing, and galaxy clustering with a coordinated panoramic vision. It's like having a single instrument that can listen to the cosmic heartbeat, feel the warping of space, and map the skeleton of matter all at once. These are not just bigger telescopes, they are fundamentally new instruments of discovery. A unified, global effort to corner the mystery. The data they will produce over the coming years offers our best chance to answer the critical questions. Is dark energy truly a constant, or does it evolve? Does its equation of state, that critical W parameter, deviate from -1? The precision will be so high that even a tiny deviation could be detected. That could rule out the simple cosmological constant and point toward dynamic theories like quintessence, or the data could solidify the constant model, forcing us to confront the fine-tuning problem with even greater urgency. We are building the ultimate cosmic detectives. Their observations will either confirm our strange, accelerating reality, as described by our current model, or they will reveal the cracks that lead to a deeper, more profound understanding. The hunt is intensifying, and the universe is about to be put under a microscope of unimaginable scale. These immense surveys are going to produce a flood of data, and the question is, how do we make sense of it? How do we test a theory about dark energy? We can't rewind the universe and run it again, but we can build a new one inside a supercomputer. That's the world of cosmological simulations. Entire digital universes built from equations and evolved over billions of virtual years. It starts with a seed. The initial conditions, they're not guesses. They're the precise, tiny fluctuations we see in the cosmic microwave background. That snapshot of the infant cosmos is the starting point. Into this virtual space, programmers code the known laws: gravity, the behavior of dark matter, how gas moves, how stars form. And then, crucially, they add a model for dark energy. It could be Einstein's cosmological constant, or a dynamic field, quintessence, or a modification to gravity itself. Each simulation uses a different recipe for that ingredient. Then they press play. The supercomputer takes over. It calculates the gravitational pull of every virtual particle on every other. It models how gas cools and collapses into the first stars, how supernova blast material back out, how galaxies merge, how clusters assemble along those vast filaments of dark matter. The simulation runs for months, tracing the evolution from that primordial soup to the present day. The result is a complete, self-consistent history. A digital twin of a possible universe. Then scientists step back. They examine their creation. They don't just look at visualizations. They perform the same measurements on the simulation that astronomers do on the real sky. They catalog virtual galaxies and measure how they cluster. They calculate the weak lensing signal. They find simulated supernova. They measure the Baryon acoustic oscillation scale at different times. They generate mock data sets, directly comparable to what comes from telescopes like Rubin, Daisy, Euclid, and Roman. The power is in the comparison. Does a universe simulated with a simple cosmological constant produce a large-scale structure that looks like ours? Does its expansion history match the supernova data? Does the clustering of its galaxies have the same statistical properties? If the answer is yes, that model survives. If the answer is no, if the digital universe looks fundamentally different from the one we observe, that version of dark energy is ruled out. It's a process of elimination. On a cosmic scale, these simulations are more than tests. They're discovery tools. By tweaking the parameters, researchers can ask what-if questions. Questions nature won't answer for us. What if dark energy was twice as strong? What if it turned off 5 billion years ago? The simulation shows the consequences. It reveals how the cosmic web would be different, how many galaxies would form, how empty the voids would become. This virtual experimentation guides theorists. It tells them which ideas are worth pursuing and which are dead ends. It turns abstract equations into observable predictions. In a real sense, these digital universes are our laboratories. The only place where we can run controlled experiments on the fate of everything. As the observational data grows more precise, the simulations must grow more sophisticated. They have to include more physics, more detail, at higher resolution. It's a race between two kinds of creation. The telescopes mapping the real cosmos, and the computers building its countless reflections. Each one refining the other, inching us closer to understanding the unknown force written into the code of reality itself. Dark energy's final outcome, it's more than a scientific prediction. It becomes a kind of philosophical reflection. For a long time, we put ourselves at the center of the story. The universe felt like a stable stage, something permanent, set there for us to explore. But this finding turns that around. It says the stage itself is active, driven by a force that has no interest in anything on it, a force that doesn't touch light or matter. That has no concern for stars or planets or life. It just exists, and it's running the show. That idea quietly questions any thought that the cosmos was built for us, that our narrative is its main point. We're in a universe where the basic rules are still being set, and we arrived late to the story. The lasting importance of intelligence, of civilization, all our art and effort, it plays out against a background that might finish in silence or just fade away. It can feel lonely, like discovering the house you're in is gradually coming undone, and you can't fix it. But inside that enormous indifference, there's another sort of meaning. That we can notice this mystery, that we can measure how space stretches over billions of years, that we build telescopes and models to ask these questions, that's our particular part. In a cosmos ruled by the unknown, we are the piece that tries to know. We aren't the center of the narrative, but we are the ones aware of it. Philosophers and scientists are now circling the same point. Not what special spot we hold, but what our role is inside a reality this strange. Maybe it's just to comprehend, to chart the shape of the dark, even as it stretches away from us. That moves the human endeavor away from cosmic importance toward a deep, persistent curiosity. Our mark might not be carved into the universe's fate, but into the path of grasping it. A path that goes on against the pull of expansion, for as long as we keep the light of questioning alive. The multiverse is one of the more provocative ideas for the fine-tuning. The logic is actually quite simple. If our universe is just one bubble in an infinite froth of others, each with its own random set of physical laws and constants, then the mystery of dark energy's value just vanishes. In most of these other realms, the cosmological constant could be enormous. It would tear space apart before anything could form, or it could be negative, causing a rapid collapse. But in a rare few, by pure chance, the number lands in that narrow, habitable window, a window where galaxies can coalesce, where stars can ignite and planets can form. We find ourselves in one of those rare, hospitable bubbles, not because the universe was designed for us, but because we could only ever arise in a place where the numbers allowed it. That's the anthropic principle. It shifts the question. It's no longer why is the constant so small, but what must the constant be for observers like us to exist? For some, that's a profound insight. A way to make sense of the seemingly impossible odds. For others, it feels like a retreat, an admission that we may never find a deeper, more fundamental reason from within our own cosmos. The debate touches the core of scientific philosophy. Is the goal of physics to find a single, elegant equation that predicts every constant from first principles? Or is our reality just one possibility in a sprawling, untestable ensemble? Dark energy sits at the heart of this. Its whisper-thin value is either a clue pointing toward a grand unified theory we haven't yet discovered, or it's a sign that we live in a much stranger, much larger reality than we ever imagined. The controversy pushes us to ask not just what the universe is, but why it is this way at all. The deepest puzzles are right in front of us. They're hidden in what we think of as nothing. That empty space has energy. That's the foundation for how we explain dark energy. But what does that mean for a vacuum to have energy? In our normal experience, a vacuum is just empty. Nothing there, but quantum physics shows something else. At the smallest scales, reality is never still. It's a sea of potential. Pairs of particles and antiparticles appear for an instant. They borrow energy from the vacuum, then annihilate and give it back. This isn't just an idea. It comes from Heisenberg's uncertainty principle, which allows these brief moments where energy conservation is broken. The vacuum isn't a still pond, it's a quantum foam, a churning, bubbling layer under everything, and all that churning, that constant appearing and disappearing, should give space itself an energy density. That's vacuum energy. In Einstein's general relativity, energy curves spacetime. Any energy does that, and this kind, if it's positive, creates a repulsive curvature. A sort of anti-gravity, so the picture is clean. The quantum vacuum isn't empty, it's active. That activity gives space an intrinsic energy, and that energy pushes galaxies apart. It fits, then you do the math, and the picture breaks. When physicists calculate the expected energy density from the quantum foam, the result is a disaster. It comes out to something like a 1 with 120 zeros after it. That's the prediction. The actual strength we see from the accelerating expansion is almost zero by comparison. It's the difference between a supernova's energy and a grain of sand. The biggest mismatch between prediction and observation we've ever had, so we're left with a brutal choice. Either our understanding of the quantum vacuum is completely, spectacularly wrong, or there's some perfect, miraculous cancellation, a symmetry or mechanism that subtracts almost all of that huge quantum energy, leaving behind only the tiny bit we detect as dark energy. The first possibility is humbling. It means when we take our quantum field theories from the particle scale up to the cosmic scale, something fails. The tools that work for atoms break for the universe. The vacuum catastrophe is a flashing sign that we're missing a crucial piece of physics. The second possibility is just as unsettling. It implies a fine-tuning of unbelievable precision. For the cancellation to leave just the tiny value we see, nature's parameters would have to be balanced perfectly. This leads some to the multiverse idea, that our universe is one of many, and we just happen to live in the rare one where the numbers accidentally allow for galaxies and life. But for many scientists, that feels like giving up on a real explanation. This is why dark energy is more than a cosmic mystery. It's a direct challenge. A screaming contradiction between our two most successful theories. Quantum mechanics rules the very small. General relativity rules the very large. Both are brilliantly confirmed. Yet they can't agree on the energy of nothing. To fix this, we don't just need better measurements. We probably need a new theory of reality, a framework that successfully joins the quantum world with gravity. A theory of quantum gravity, that's the goal, and dark energy, the push of empty space, is its biggest clue. The energy of nothing might be the key to everything. The idea of the vacuum, this profound mystery, it tends to drift into popular imagination, and it often loses its scientific shape when it does. In movies and stories, you'll see the term dark energy cast as something else. A shadowy, conscious power, a cosmic villain with its own will, but it's crucial to separate that fiction from the fact. The fact is more compelling. Dark energy isn't a substance you could touch. It's not a beam you could block. It doesn't interact with light or matter, not in any way we've detected. It's a property, a characteristic of space itself, so you should think of it not as an actor on the stage, but as a fundamental rule of the stage, a rule that says the stage has to constantly grow larger. The dark in its name, that has nothing to do with morality. It doesn't mean malevolence, it just means we can't see it directly. It's dark to our telescopes. We only see it revealed by its gravitational effect on the whole cosmos. It is mysterious, but it's not malicious. It has no intention. It just is, and that clarity matters. Because it shifts our awe from a place of fear to a place of curiosity. When we hear dark energy makes up most of the universe, it's easy to picture a looming, alien presence. But the reality is subtler, more astonishing in a way. It's the quiet hum of nothingness that pushes everything apart. Now, confusing it with dark matter, its cosmic cousin, that's another common mix-up. They share the word dark because both are invisible to light, but their roles are opposites. Dark matter pulls. Its gravity is the cosmic glue. It holds galaxies together. Dark energy pushes. It's the cosmic pressure that stretches the universe apart. One builds structure, the other suppresses it. They are the two great unknowns in our cosmic ledger. One sculpts the islands of matter, the other governs the sea of space between them. Dispelling these myths, it's not just about scientific accuracy, it's about grounding our wonder in the actual phenomena. The real story of a uniform energy inherent to the vacuum, a force that waited 9 billion years to reveal its dominance, a mathematical constant that might decide the fate of all existence. That story doesn't need fictional embellishment. It's strange enough on its own terms. By understanding what dark energy is not, we clear a path to genuinely grapple with what it is, and that allows the public discussion to move beyond sensationalism and into the realm of practical implication. What does it mean for our future that the fundamental fabric of reality contains this expansive tendency? The answer begins not with speculation about sentient forces. It begins with the patient collective work, observation, simulation, and theory. Our journey to comprehend this force, it's a testament to human reason. Probing the deepest rules of the cosmos, a search for truth in the expansive dark. The search for this cosmic force is reshaping our tools for seeing. We can't touch dark energy, but the effort to measure it pushes engineering to its absolute limits. The telescopes built for this are marvels of precision. Their mirrors have to be polished to near-perfect smoothness. Their cameras have to detect the faintest whispers of light from galaxies billions of light years away. The sensors on the Euclid and Roman space telescopes are so sensitive they can measure the tiny distortion in a galaxy's shape from weak gravitational lensing. This isn't just astronomy. It's an extreme form of measurement science, and the advanced optics developed to correct for atmospheric blurring in ground-based observatories are now finding uses in medical imaging, letting doctors see finer details in the human body. The machine learning algorithms created to sift through billions of celestial objects are the same kind of artificial intelligence that can analyze medical scans for early signs of illness. The pursuit of the cosmos sharpens our vision here on Earth, but the greatest technological promise isn't in the spin-offs, it's in the potential for a fundamental breakthrough. Every deep revision of our physical laws has unlocked unforeseen capabilities. Understanding electromagnetism gave us the radio, the power grid, global communication. Harnessing quantum mechanics brought us the transistor, the laser, the entire digital age. Each time we cracked a core mystery of the universe, it didn't just satisfy curiosity. It gave us a new set of tools to reshape our world. Dark energy is the next great frontier. It's a glaring signal that our two foundational theories are incomplete. Solving this puzzle likely means discovering the missing link between the quantum world and gravity. It means a theory of quantum gravity. What could that make possible? We can only speculate. Our speculations sound like science fiction, but consider the pattern. Relativity corrected Newton's laws and later became essential for GPS. Quantum theory explained the atom and later gave us the semiconductor. A successful theory of quantum gravity would describe the fabric of space-time itself at the most fundamental level. It might reveal aspects of reality we consider immutable constants. Could it lead to insights about energy, or the stability of matter, or the nature of information? The technologies born from such a revolution are, by definition, beyond our current imagination. They belong to a civilization that has finally read the full set of instructions for reality. Our task now is to gather the clues. Each precise measurement from these telescopes, each simulation of a digital universe, is a line of code we are slowly deciphering. The distant promise isn't a device that controls dark energy. It's the profound and practical wisdom that comes from finally understanding why the universe contains such a force at all. Ancient skywatchers saw a celestial dome, a sphere of fixed light turning above a stable Earth. That was the first cosmic model, a story of permanence. Then came the shift. Copernicus moved Earth from the center. He put the sun there instead. It was a conceptual earthquake. The universe was no longer built around us. It became a mechanical system governed by mathematics, and that set the stage for a new kind of questioning, not just where things were, but how they moved. And why Kepler gave us elliptical orbits, Newton gave us universal gravity. The cosmos became a grand, predictable clockwork, but the stage itself, the infinite space containing the stars, that remained static. Eternal, this was the accepted view for centuries, a universe that was essentially complete, unchanging in its large-scale structure. The fixed stars were truly fixed. That idea comforted and it constrained. It suggested a kind of cosmic finality. Then, in the early 20th century, the stage began to move, first with Einstein's relativity, which described a dynamic, flexible spacetime. But even he initially clung to a static universe. He inserted his cosmological constant as a fix. Then, just a decade later, Edwin Hubble's observations shattered that stillness. The galaxies were fleeing, the universe was expanding. That discovery rewrote the narrative from permanence to evolution. The cosmic clockwork had a beginning. It was growing. The next logical step was to forecast its future. With gravity as the only major force, the expansion had to be slowing. The universe would coast to a stop. That became the standard model for most of the 20th century. A universe born in fire, now gradually winding down. Every observation seemed to fit. Until it didn't. The search for that slowdown, using the light of dying stars as cosmic mile markers, led to the opposite conclusion in 1998. The expansion wasn't slowing, it was speeding up. That moment stands as a stark line, a before and after. Before, we thought we understood the dominant forces. After, we knew we were missing something that made up most of reality. Each major pivot in this story followed the same pattern. A comforting assumption is challenged by a precise measurement. The challenge forces a new picture, often a stranger picture of reality, and that new picture immediately presents deeper questions, more fundamental questions. We are living in one of those pivotal moments right now. Dark energy is our generation's great unknown, just as the fixed stars weren't fixed and the static universe wasn't static. Our accelerating cosmos tells us the story is far from over. The timeline doesn't end with a question mark. It continues with a global effort with telescopes and computers. striving to turn that question mark into the next chapter in humanity's oldest story, the story of looking up and daring to ask, what is this place? And what are the rules that govern it? This cosmic search goes beyond astronomy. The dark energy mystery sends ripples across all of human knowledge. It pulls in experts from different fields to work on the same puzzle. The problem is a collision of scales. To explain why empty space pushes, you need particle physics. Theorists have to grapple with the quantum vacuum, that seething foam of virtual particles. There's a mismatch. Their predicted vacuum energy is enormous, and what we observe is tiny. It's the single greatest crisis in fundamental physics, a direct challenge. It demands new ideas to bridge the quantum world with gravity. So cosmologists provide the constraints, the precise rate of acceleration, the geometry of the universe. Particle physicists have to build models that match them. Each new, tighter measurement from a telescope like Euclid rules out whole families of theoretical ideas. It guides the search. The sheer volume of data creates another frontier. We're gathering petabytes of information. Making sense of it requires a new kind of mathematics, a new computer science. Statisticians develop methods to extract weak signals from immense noise. Computer scientists design algorithms to identify billions of faint galaxies, measure their shapes, map their distortions. The machine learning techniques pioneered for this cosmic cartography are now being adapted for medicine, finance, climate science. The challenge of seeing the universe has sharpened our ability to find patterns in any complex data. And the implications reach into philosophy, reframing questions about our place in a cosmos governed by an indifferent force. But the interdisciplinary impact is also practical. Consider the global effort behind the Vera C. Rubin Observatory, the legacy survey of space and time. It involves hundreds of scientists, engineers, software developers from dozens of countries. Building the telescope, creating the data pipelines, planning a decade of observations. It's a feat of international cooperation. It fosters shared technological advancement. It trains a new generation of researchers in cutting-edge skills. It creates a monumental scientific resource that will be used for decades. The quest to understand dark energy builds bridges between academic disciplines and between nations. It shows how a fundamental question about reality can unite diverse talents, driving innovation that benefits society far beyond the walls of any observatory. In chasing the force that tears the universe apart, we are pulling the threads of human knowledge closer together. The greatest stories in science are still being written. And dark energy is one of them. This isn't just for people in observatories. It's a living mystery. It can inspire the next explorers. A student opens a textbook and it can feel like history. The laws seem settled, the big discoveries are done, but dark energy breaks that. It's an open question printed across the cosmos. It shows the universe still has profound secrets. And the people who will find them might be in a classroom right now. This is where learning changes. It goes from memorizing facts to joining a quest. A planetarium can show the known stars, and it can show the invisible force pushing them apart. A documentary can frame the search as a detective story. The clues are in ancient light, in galactic patterns. In a classroom, you can use a balloon and dots. You can model the accelerating expansion. An abstract force becomes tangible. The goal isn't to make every student a cosmologist. It's to ignite a spark of wonder. The spark comes from a realization. Some of the most fundamental questions are unanswered. What is space? What is the fate of everything? What makes up most of reality? By sharing this journey, we invite young minds in. We show them science isn't a static monument. It's a construction site. It's dynamic. It's collaborative. The blueprints are being drawn as we build. The students captivated by this today will bring new perspectives tomorrow. They might develop the new math for quantum gravity. They might engineer a more sensitive telescope, one that finally detects a change in dark energy's strength. Or they might write the simulation code, the code that reveals a pattern everyone else missed. This outreach is an investment. It's for the long-term survival of curiosity. It makes sure the torch is passed forward, the torch of questioning, of looking up and daring to wonder. The solution to dark energy may not come from our current scientists. It may come from a mind being inspired right now by a planetarium show, by a documentary, by a teacher who shared the story of the unknown force tearing the universe apart. Our job is to hand them the map, to point to the blank spaces, and to say we haven't finished this yet. Will you help us look? The scale of the universe can shrink our daily concerns. But the cost of studying it is enormous. Public funds build new telescopes, launch observatories, operate data centers. That raises a hard question. With so many pressing issues here, disease, environmental collapse, should we spend billions to study the far edges of space? It's a serious question, one the scientific community has to engage with, and the argument for these projects starts with a basic point. This need to explore, to find our context, it isn't extra. It's central to who we are. That curiosity has always driven progress. The search for pure knowledge, for answers to fundamental questions, it tends to create unexpected, practical gains. You can't always see them coming. The tools built to see the cosmos often circle back. Advanced optics end up in hospitals, improving scans. The software that maps billions of galaxies can also model climate systems or untangle social networks. And the global partnerships themselves, they forge diplomatic ties. They train scientists to handle complex, worldwide problems, but the balance is still delicate. It's not an either-or choice. It's a continuous discussion about scale, about priority. Justifying a space telescope means pointing to its twin returns. The expansion of human knowledge and the concrete spin-offs that benefit life on Earth. The job is to communicate that value clearly, to show responsible use of public trust and money. This isn't about protecting an isolated endeavor. It's about weaving the cosmic search into the wider human effort, to demonstrate that looking out at dark energy is also a way of looking in. It builds our collective skill. It inspires the next problem solvers. It reminds us that our biggest challenges, whether on this planet or beyond, they're met with the same instrument. The persistent, hopeful use of human curiosity. There's a horizon we can't cross. It's not a hill or a mountain. It's a boundary in space and time. Light has a finite speed. And the universe is expanding, accelerating. So there's a fundamental limit to what we can ever see. The cosmological horizon. Past a certain distance, galaxies are moving away so fast their light will never reach us. The space between us and them is stretching faster than light can cross it. They're lost, not because our telescopes are weak, because physics puts them forever out of reach. That raises a humbling question. Could the truth about dark energy be out there, in those hidden places? Could the force tearing the universe apart have started in a part of the cosmos we're barred from seeing? The conditions that set dark energy in motion, the reason for its strength, those answers might be written in chapters of cosmic history that have already drifted past our event horizon. We're detectives, but the most crucial pages of evidence have been burned away by the expansion of reality itself. So there's this staggering possibility. Some cosmic truths may be permanently veiled, not by a lack of ingenuity, by the immutable architecture of the universe. The acceleration dark energy causes is what hides its own origins from us. It's a cosmic catch-22. We study the force by watching its effects on the distant universe, yet that same force is erasing the most distant evidence from our view. Every second, more galaxies cross that horizon and vanish. The universe isn't just expanding, it's forgetting, and we're watching it forget. But this limit isn't just a barrier. It's an insight. It teaches us the universe isn't an open book. It has a structure that conceals parts of itself. The cosmological horizon is a fundamental feature our theories predict. Confirming it through observation is a triumph. It tells us the cosmos has a shape, a fate that includes permanent isolation. With all our technology and curiosity, we might be like islanders in an infinite ocean. We can map our own archipelago, but the vast open sea, other distant island chains, they remain forever beyond the curve of the world. That doesn't make the search futile. It means the search has boundaries. Our goal shifts from hoping for a complete answer to mapping the shape of the question itself. Understanding what we cannot know is a form of knowledge. It defines the playing field. The universe is under no obligation to be fully comprehensible to the minds it accidentally creates. And in that realization, there's a strange freedom. We're freed from the expectation of a final, complete theory. Instead, we're invited into an endless conversation with a reality that will always have more to reveal. And more to conceal. The unknown force may keep its deepest secrets, but in chasing them to the very edge of sight, we learn the most important secret. We learn the shape of our own ignorance. The mystery of dark energy belongs to anyone who's ever looked at the stars. The scale is cosmic, but the story is human. It's written in our desire to know, in our refusal to accept that the biggest questions are off limits. That drive to look into the dark and ask why. It connects a scientist at a supercomputer to a child with a telescope. The same curiosity is there. When you step outside on a clear night, you see that star-filled blackness. That's the stage. The light from those stars has traveled across an expanse that's been stretched and shaped by the very force we're trying to understand. So your act of looking up is a connection, a personal connection to the grandest puzzle. It means we're not just passive observers of a fixed cosmos. We're participants in a story that's still unfolding, a story where the stage itself is alive, and that changes the feeling of cosmic smallness. It's not about being insignificant. It's about being the part of the universe that became self-aware, the part that can wonder about its own origins, its own fate. That ability to feel awe in the face of the unknown, that's our contribution. It ties our moment of consciousness to the billion-year saga. So the future of this exploration, it isn't just about bigger telescopes. It's about nurturing that wonder in the next generation. Making sure the torch of curiosity is passed forward, so the story continues. The light is coming. In the next 10 years, the data from Euclid and Roman, from Rubin and Daisy, it's going to change our view completely. It's not a sketch anymore, it's an ultra-high-definition map, and it's a new kind of evidence. It lets us ask sharper questions. The first one, the most critical one, is about dark energy. Is it constant? Is it just a fixed property of space, Einstein's cosmological constant? Or does its strength change over time, like in the Quintessence model? Right now, our measurements say it's consistent with a constant, but the uncertainty is large. There's room for it to be something else. These new surveys, they're going to shrink that uncertainty. Dramatically, they'll measure the expansion history of the universe, the growth of cosmic structure with percent-level precision. It's like trying to hear a faint, steady hum in a noisy room. For years, we've just confirmed the hum is there. The new instruments are like noise-canceling headphones. They let us listen for the tiniest waver in that tone. Any detectable change would be revolutionary. It would rule out the simple constant forever. Then there's a second question, a possible hidden relationship. Does dark energy interact with dark matter? In the standard model, they're separate. One pushes, the other pulls. They coexist, but they don't communicate. But what if that's wrong? What if there's a subtle exchange, an energy transfer between the invisible scaffolding and the repulsive vacuum? An interaction like that would leave a fingerprint. A unique one on how galaxies cluster across different times in history. Those immense three-dimensional maps from Dacey and Rubin, they're designed to find that fingerprint. They trace the cosmic web across billions of years, watching for any structural oddity, anything that suggests these two dark components are talking to each other. And then there's the most radical alternative, modified gravity. This idea asks us to reconsider a pillar. Maybe there is no dark energy. Maybe, on the largest scales, Einstein's theory of gravity just needs a tweak. A slight alteration in how gravity works over cosmic distances that could mimic the effects of an accelerating expansion. It's a bold claim, and the new data will test it. Mercilessly, weak gravitational lensing measured by Euclid and Roman with exquisite care is a direct probe, a probe of gravity's behavior. If gravity is being modified, the way it distorts light from distant galaxies will follow a different pattern. Different than if dark energy is a separate force. The surveys will measure millions of these distortions. They'll either confirm the dark energy framework or force a rewrite of gravity itself. These milestones, they won't deliver a final answer, not on a silver platter. Science rarely works that way. Instead, they'll perform a great act of elimination. They'll definitively rule out whole classes of theories. Swaths of the theoretical landscape will get cleared away. What remains are the paths that actually match the data. That narrowing is how we make progress. It guides the theorists, tells them where to focus. It points toward a more complete theory, and likely a stranger one. We're building filters to strain the ocean of data, hoping to catch a few precious grains of truth. The next decade isn't about finding the answer. It's about learning how to ask the perfect question. History shows something about mapping the cosmos. The universe is full of surprises. Every time we think we've got the big picture figured out, a new piece of data comes along and changes it. The shift from a static universe to an expanding one was a shock. Finding the cosmic microwave background, that ancient whisper of creation, was a stunning confirmation of a wild idea. And then dark energy, this force tearing everything apart faster and faster, that completely reversed what we thought we knew. These breakthroughs didn't come from proving some small detail. They came from data that just wouldn't fit the story we had. That pattern is clear. Our deepest insights happen when the universe corrects us, politely but firmly. And that's not a flaw in science, it's how discovery works. It means that as we build more powerful tools, we have to practice a certain kind of humility. We have to stay open to the idea that our current understanding of dark energy could be wrong. The models we have, with their precise numbers and elegant equations, they're our best maps. But they're not the territory. The next big finding from a telescope like Roman or Euclid might not just tweak a number. It could point somewhere we haven't even thought to look. Maybe dark energy isn't an energy field at all. Maybe the data pushing galaxies apart is actually telling us that our theory of gravity, Einstein's theory, needs to change on the largest scales. What if gravity behaves differently in the vast emptiness between superclusters? That idea, modified gravity, challenges a foundation, but it's a real possibility that new measurements will test. Or maybe the acceleration is a clue to a deeper rhythm, evidence for a cyclic universe where expansion leads to contraction in an endless cosmic heartbeat. In that model, what we call dark energy might just be the gentle crest of a wave, a phase in a cycle so long we mistake it for a one-way trip. These aren't fringe ideas. They're serious, competing stories born from the same stubborn data. The only thing we know for sure is that the cosmos is still keeping profound secrets. Our map still has blank spaces labeled "Here be dragons." So our job is to build the best compasses we can and sail toward those blanks with curiosity, not certainty. The biggest discovery of the next decade might not be the nature of dark energy. it might be realizing we've been asking the question the wrong way all along. The universe's next surprise is waiting. Our job is to be ready to listen when it speaks. We began with a discovery. The universe is expanding, and that expansion is speeding up. That fact changed everything. It pointed to a force in space itself, dark energy. Most of the universe is made of it. It overcame gravity, and now it controls how everything ends. A big freeze, or maybe a big rip. The outcome depends on what this force really is. We looked at the evidence: supernova, the cosmic microwave background, the large-scale structure of galaxies. They all tell the same story, but we still don't know what it is. Is it Einstein's cosmological constant, just a feature of empty space? Is it a new kind of field, or is it a sign that gravity itself is wrong? This isn't a small question. It's the biggest problem in cosmology. It's about connecting the very small to the very large. The search for an answer is a human story. It's curiosity. It's a global effort with different fields of science working together, building better telescopes, running simulations. It shows our need to understand where we are. We don't know what dark energy is yet, but the search tells us something. We are the part of the universe that's aware of its own story. And we want to know how it ends, so when you look at the night sky, see it differently. Those stars, those galaxies, they're moving. They're being pushed apart by this expansion, by this force we're trying to find. That view connects us to the puzzle.